Welcome back to the deep dive.
Good to be here.
Today, we're getting into, well, a really core skill for anyone working with control systems. It's that translation process, right? Taking the logic, the schematic diagram,
Mm-hmm.
and turning it into actual physical wiring that works.
Exactly. It's where the plan meets the panel, you could say. We're diving deep into diagram conversion,
Yeah.
how you take that often quite complex electrical schematic
Yeah, they can be dense.
and turn it into a wiring diagram that an electrician can actually use to install everything correctly. And just as importantly, why you sometimes need to go back the other way.
Right. So if you're out there designing, installing, maybe commissioning, or just finding yourself troubleshooting a control system at 2 a.m.,
We've all been there.
oh, yeah. Then this deep dive is definitely for you. We've lined up the key info, the methods, the compliance rules you absolutely need to know, and also some really practical efficiency tips that experienced folks use to save time and money.
Yeah, our goal today is really to give you that blueprint for converting diagrams both ways. We want you to walk away understanding those critical rules like what really separates a node on a schematic from a physical splice point.
Uh,
Getting that right saves, well, potentially thousands in troubleshooting later.
and ensures you're actually compliant, which is huge.
Absolutely critical.
And I think the key insight here, maybe the big picture, is that this isn't just about redrawing lines, it's a transformation process. You're taking complex logic
Sometimes really complex logic.
and making it physically manageable, readable in a wiring diagram format
Yeah.
that lets you install precisely, safely, and makes it maintainable down the line.
Exactly. So let's get into it.
Okay, let's start with the most common direction, schematic to wiring. So moving from the logical sequence of operations
So how it should work.
to the actual physical connections between all the equipment, the wires and the conduit.
And right off the bat, the first thing you have to think about is function. Does the wiring you're planning actually maintain the intended operation? Especially, and this is non-negotiable, the safety functions.
Okay, so give us an example. What's a critical functionality mistake that can happen here?
The classic one is the emergency shutdown, the ESD circuit.
Yeah.
Its entire purpose is to stop everything.
Right. Unconditionally.
So if during that conversion from schematic to wiring, you accidentally draw a parallel path, maybe around one of the ESD push buttons,
Uh-oh.
you've just bypassed your safety system. It looks fine maybe on paper if you're not careful, but it won't work when needed. It's a huge liability. The conversion must preserve or even enhance safety, never compromise it.
That makes total sense. Safety first. So once we've double-checked safety, the sources lay out a pretty clear procedure. It sounds like it's really about being methodical.
It absolutely is.
Yeah.
Slow and steady wins the race here. First, you sketch out the physical locations. Where are these components relative to each other in the real world? Label them clearly, M1 for the motor starter, PSH for the pressure switch high, whatever the standard is. Then critically, add the terminal numbers for every connection point, 95 and 96 on the overload, A1 and A2 for the coil,
All of them.
every single one. It prevents hookup errors.
And then step 3, this seems crucial, focusing on one conductor at a time.
Yes. This is where people often get tangled up. You trace one entire conductor path on the schematic, including all its parallel branches, and transfer all that information to your wiring diagram. Don't jump around.
So finish wire 1 completely before you even think about wire 2.
Exactly. And then step 4, immediately mark off that conductor on the schematic. Put a highlighter through it, tick it, whatever works. Just make it obvious it's done so you don't lose track.
Okay, this brings us to what feels like a major aha moment from the source materials. The difference between a schematic node and a physical splice. Why is this distinction so important for compliance?
Ah, yes. This is fundamental. Because your wiring diagram needs to reflect the physical reality of the installation, and codes like the Canadian Electrical Code are very strict about this.
How so?
You can only terminate or splice wires at proper designated locations. Think screw terminals on a device, terminal blocks in a junction box, maybe a bus bar, places that are accessible and designed for connections.
So that little dot on the schematic, the node, just shows that multiple wires are electrically connected at that point in the logic.
Right, logically connected.
It doesn't mean I can just twist wires together with a wire nut and leave it floating inside a conduit or tucked away somewhere inaccessible.
Absolutely not. That's a code violation waiting to happen, and a nightmare for troubleshooting later. If your wiring diagram shows a connection point, it must correspond to a physical approved terminal or splicing device in the actual installation. That's the key. It has to be real and accessible.
That's a fantastic point. It's not just neatness, it's safety, compliance, and maintainability. Okay, let's make this concrete. The materials mention a basic three-wire control circuit. Can we trace the logic quickly?
Sure, it's a standard motor control circuit. So you press the start button. That completes the circuit to the control relay coil, what's called CR. The coil energizes.
And CR has contacts associated with it, right? Like
Yeah.
CRA and CRB?
Exactly. When the CR coil pulls in, its contacts change state. CRA is a normally open contact wired in parallel with the start button. It closes.
Ah, the seal-in or holding contact.
Precisely. It keeps the CR coil energized even after you let go of the start button. That's the memory. At the same time, another normally open contact, CRB, also closes.
And that might turn on a pilot light or enable the next step.
Yep, maybe it energizes a pilot light to show the motor is running. Then the stop button, which is normally closed, is pressed.
Breaking the circuit.
It breaks the circuit to the CR coil. The coil de-energizes, and both CRA and CRB contacts open again, dropping the seal-in and turning off the pilot light. The schematic shows that perfect sequence. The wiring diagram has to make it happen physically.
Okay, that makes sense. So that leads us naturally to the other direction. Why would you ever need to convert a wiring diagram, the physical layout, back into a schematic?
Great question. Because, honestly, wiring diagrams are usually pretty terrible for figuring out how something actually works.
Really? Why is that?
They show you where the wires go, which is essential for installation. But they prioritize physical location over logical flow. If you're troubleshooting a complex panel, looking at the wiring diagram can feel like staring into a spaghetti mess. You can't easily see the sequence of operations.
Ah, so the schematic cuts through the physical clutter to show the pure logic.
Exactly. Converting back to a schematic turns that potentially confusing physical layout into a clean, organized roadmap of the control logic. It makes troubleshooting vastly easier.
Okay, so if we're creating that schematic for troubleshooting, we need clear, standardized labels. What are the main standards for identifying devices?
There are two big ones you'll see constantly. In North America, it's often NEMA standards. So you'll see things like M1 for a motor starter, CR for a control relay, AWEL for an overload relay.
Okay.
Internationally, and increasingly common everywhere, you have IEC standards. They use slightly different letters. K is often a general relay or contactor, KM specifically for a motor contactor, F for a fuse or overload device, S for a switch. Knowing both helps.
And pilot devices too, like push buttons or switches, they get functional labels.
Yeah, which is really helpful. You'll see things like PSH for a pressure switch high or LSF for limit switch forward. It tells you what that device is doing right there in the label. Very useful.
Now, you mentioned traceability earlier. The real backbone seems to be how we label the conductors, the wires themselves.
Oh, absolutely. This is probably the most critical rule for understanding logic from either diagram type. The rule of conductor labeling. Simple, but powerful. A single conductor label, whether it's a number, letter, or even a color code, applies to that entire electrical node. All branches, all connection points that are electrically common.
So if wire 1 goes from the power source and splits off to feed 3 different switches,
All three of those wire segments are still labeled 1. They are electrically the same point until they pass through something that changes the state.
like a contact or a switch.
Exactly. If wire 1 goes into, say, normally closed overload contacts 9596, the wire coming out of terminal 96 must have a new label, maybe 2 in us. That change in number signifies that something has happened logically. The state could be different after that device. The numbers trace the flow.
So what's the biggest mistake people make with wire numbers that just destroys that traceability?
Inconsistency is the killer. Using the same number for wires that are actually isolated by a transformer, for instance. Or maybe changing the number randomly mid-run without passing through a device. If you see wire 5 suddenly become 6 for no reason,
You've broken the chain.
you've broken the logical chain. When you're converting from wiring back to schematic, you have to be absolutely rigorous about applying this rule correctly. Find all points connected to wire 1 on a wiring diagram. Draw them all connected on the schematic, and only change to 2 minis after it passes through the first device.
Which leads nicely into verification. How do we double-check our schematic conversion is accurate?
There's a great field technique. Count the connection points.
How does that work?
On the original wiring diagram, or even physically on the panel, count every single terminal or connection point that a specific conductor touches. Let's say conductor 1 touches 6 points, L1 power, a pilot light, 2 AL contacts, an M contact, and maybe a PDS contact.
Okay, 6 points.
Your newly drawn schematic must show exactly 6 connection points for that same conductor 1. If you only have 5, or if you have 7, you know you made a mistake somewhere in translating the connections. It's a simple but effective cross-check.
That's really practical. And when drawing the schematic itself, there are layout conventions for clarity, right?
Yes, standard practice makes them much easier to read. Draw the power rails vertically, L1 or positive on the left, neutral or negative on the right. Show the voltage.
And component placement.
Loads, things like relay coils, motor starter coils, pilot lights. Solenoids, they go on the right side near the neutral rail.
Okay.
Operating devices, switch contacts, relay contacts, push buttons, limit switches, they go on the left side, between the load and the hot rail.
And the goal is clarity above all.
Absolutely. You often have to rearrange the components logically compared to their physical layout. Eliminate crossing wires as much as possible. The schematic should clearly illustrate the sequence of operation, even if it means devices aren't shown in their physical order. Function dictates schematic layout.
Okay, this is great. We've covered functional accuracy, traceability through labeling, but installation isn't just about making it work, it's about doing it efficiently. Let's talk time and money.
Right. Moving from just does it work to how efficiently can we install it.
Why does the physical order of components matter if the electrical sequence remains the same? We established function is king.
It is, functionally. Let's be clear. Series components must stay in series. Parallel components must stay in parallel. You can't wire 2 stop buttons in parallel and expect it to work safely.
Definitely not. That defeats the whole purpose.
But within a series chain, like several emergency stop buttons down a conveyor line, the electrical function is the same, regardless of which stop button comes first in the chain.
Okay, electrically, the order doesn't matter for series stops.
Correct. But physically, the order dramatically impacts the amount of wire you need to pull.
Ah, see where this is going. Explain that.
Think about it. You have stop button 1 near the start of the line, stop button 2 in the middle, stop button 3 at the far end. They all need to be wired in series. The most efficient way is to run the wire from the panel to the closest button first, SB1, then from SB1 to SB2, then from SB2 to SB3, and then back.
Makes sense. Minimize the distance.
If instead you followed maybe just the numerical order rigidly and ran the wire all the way down to SB3 first, then back to SB1, then over to SB2, you're adding a huge amount of unnecessary wire length. You're looping back and forth.
So for series circuits, physical proximity dictates the optimal wiring path to save conductor. The source materials actually put numbers on this, comparing 2 wiring layouts.
Yeah, it's a really clear example. They showed one layout, wiring A, figure 7, maybe just following a standard but less optimized path. It used 7 conductors running, I think it was 40 meters between 2 push-button stations, plus another 5 conductors running 20 meters from the starter to the first station.
Okay, what did that add up to?
That came out to 380 meters of control wire total. 7 by 40 meters plus 5 by 20 meters equals 280 plus 100 equals 380 meters.
And the optimized version.
Wiring B, figure 8.
Yeah.
By simply rethinking the physical route of those series connections to hit the closest points first, they managed to reduce the number of conductors needed between the stations from 7 down to 6.
Okay, one less run between stations. What was the total wire length then?
That dropped the total length to 340 meters. 6 conductors by 40 meters plus 5 conductors by 20 meters plus 240 plus 100 equals 340 meters.
Wow, so just by optimizing the physical path for those series wires, they saved 40 meters of conductor.
Exactly, 40 meters. Now scale that up to a big industrial project with kilometers of control wiring. That translates directly to significant material cost savings, plus the labor saved pulling and terminating that extra wire. It's real money back in the project budget.
That is a fantastic, tangible reason why planning the physical order matters so much. Even when the electrical function allows for flexibility, it's pure efficiency.
It really hammers home the point.
Okay, so let's recap the big takeaways. First, schematics are for logic, wiring diagrams are for physical location, and things like proper splicing and termination are critical for compliance and safety.
Got it. Second, conductor labeling is the key to traceability. Same number for the whole node, changes only after passing through a device. Cap connections to verify.
Right. And third, optimizing the physical order of series components, routing to the closest first, directly cuts down on wire usage and saves installation costs, even if the electrical sequence is the same.
Nailed it. Those are the core principles.
Which brings us to our final thought for you, the listener. We learned that for series devices like stop buttons, the physical order is critical for saving wire. But for parallel devices, like multiple start buttons or indicator lights running off the same signal, the physical order doesn't change the electrical function at all.
Interesting point.
So imagine you're building a huge control panel Hundreds of parallel outputs, indicator lights maybe, showing different machine states. Electrically, the order you wire them in parallel doesn't matter. But thinking about the principles we discussed, conductor numbering, minimizing wire length, clarity, how could applying those ideas to the physical layout of those parallel wires dramatically simplify things for the next person who has to troubleshoot or modify that panel years later?
Even though the function doesn't require it. How can neatness and logical physical layout pay off in the long run for parallel circuits?
Exactly. Something to think
Exactly.
about next time you're wiring up a panel.